and I invite Arkady Vainshtein, who will continue the issue of gravity and other issues of this talk. Please.
Just a moment.
Valentin Ivanovich, you should stop to share your screen. Yeah. And now, Arkady Osifovich. Yes, yes, we see everything. Yes, thanks.
Okay. Can you see it?
Yes, yes. Fine.
The only problem is that if I'm using this full screen mode, then I cannot show a cursor. Is it okay? Because a cursor does not work in Keynote in this form, but I can, okay, I probably do not need it. Okay, let me try. So first of all, my thanks to organizer, in particular to Oleg, for inviting me to speak on this occasion, you know, about hot problem of strong interaction. Okay, no, I mean, the title Massive Gravity, you know, sounds very far away from, you know, the topic of discussion, but okay, still, but it's not far away from Valia, you know, because and I will try to start from, you know, my kind of sharing my recollection of our interaction, which was kind of probably example of strong interaction. And okay, and you will see in massive gravity it also shows up. Okay, so I mean, it's the session name is anomalous transport phenomena, but I would attribute this anomalous transport phenomena to Valia himself. I mean, not so maybe it was also chiral and there were some volticity there, but you know, talking about, you know, his 80th birthday, which we are celebrating, you know, I kind of, for me, it's difficult to avoid about talking of myself, because I believe that the reason, to some extent, you know, my name is because of Valia, you know, that essentially the whole, you know, my career in physics is due to him. So in I do not, so it was indeed extremely strong effect. Okay. And that's why I'm trying to start with some recollections of no, I mean, of our interaction, which started like 55 years ago, 1965. I came to ITEP as a graduate student. I was graduate student in Budkevi Institute in Novosibirsk, but my PhD advisor was Boris Lazarevich Yoffe, who was in ITEP, and you know, actually it was originally it was Viktor Mikhailovich Galitsky, who was my university advisor in Novosibirsk, who recommended me to Pomeranchuk group. So when I came, Pomeranchuk was still, I mean, actually I overlapped with him, you know, and we started, you know, our interaction on this mansard level of ITEP building, where it was Valia Zakharov, Sasha Dolgov, Alyosha Kaidalov, and we started the soft pine, which was a new subject at that time. You know, I mean, a particular. I mean, okay, we did not publish. I believe our first publication was 67, but still we discussed a lot. In particular, it was still Pomeranchuk who was, you know, kind of asking questions and leading this discussion. And to show, no, I mean, this kind of some certain moments of this, let me say that, you know, I remember that at that time, Mari Gelman was propagating the idea about this SU3 cross SU3 symmetry as SUC algebra, and which kind of appears naturally in the limit where you have massless quarks. However, the idea that quarks are massless or close to massless at that time was, the region object, I mean, that there is some kind of a conservation of axial current was absolutely not accepted, I mean, by most of physicists at that time. And while Gell-Mann insisted on this, he never referred to this spontaneous breaking of chiral symmetry appears in the form of Gauss-Lorentz particle, while he was the author of this famous paper with Levy about this partial conservation of axial current. And I remember when we were doing this, I was kind of extremely surprised by that he never did it. So later on, I actually asked Murray, why he insisted on this algebra SU3 and not using any kind of argument in favor, which he could use this non-Boolean Lazini and all this stuff. Okay, and I suggested that he has direct, direct interaction with heavens. Okay, so Gell-Mann refused that he had it, but what I'm trying to say is that Weyl is a person of the same kind. So the way he kind of picking up this kind of, he has particular kind of gut feelings what is important and what is relevant, and even if he does not know how to kind of argue for this, he would not stop until to persuade in the idea. Okay, I mean, example was immediately after this was, say, this idea, in kind of the very beginning in 70s, where this idea that quarks are almost masses, and there is a chiral symmetry became penetrate into the community. And Weyl was the one who kind of appreciated in full strength, and it is realized in our activity associated with this strong correction to weak interaction, particular to enhancement of delta I equal 1/2. I mean, in weak non-leptonic decays, which kind of later so we use operator product expansion, and the parts that quark are masses or almost masses were important for this enhancement of certain operators, which later got the name penguins. So okay, and it was about that time when Viktor Novikov and Misha Schiffman joined the activity. Okay, then it was, say, a lot of other activities, say, including this Higgs interaction with hadrons, when this standard model appears, germanium, when it was discovered, instanton. Okay, then we started to apply some rules for germanium first, and QCD some rules. But again, it was example where, how to say, it was, if it would be not Weyl's insistence that we should go with all these ideas all the way to the end, this QCD some rules would not show up. So it's not probably very visible from outside, but it was very visible for me, So okay. No, another example was this supersymmetry when we started this study, applied this also instantonic stuff to supersymmetry, and Weyl came with the idea that instanton looks like they are breaking supersymmetry. Okay, so we spent kind of extremely I don't know, more than a year, I think, trying to resolve the problem. We published some strange paper, whatever, but it was kind of this kind of non-stop brainstorming. So until we will find out what to do, and you know, it is a way, you know, when we kind of eventually came to this result for an SVZ beta function and this Brane condensate. Okay, so it is, you know, I mean, something which I am trying to share with you to show that you know, that it is absolutely unique for person. And okay, and I am not sure about his heavenly interactions, but certainly, I mean, he, as we see, he is still continuing, you know, in very much similar way. So okay, so so let me wish Valia many more happy returns of the day and continuing of this activity, of your activities for many more years as well. So thanks. And I don't know, as I said, I owe you so much that, you know, I cannot kind of really put it in proper words, but I certainly feel it. And okay, anyways, thank you very much for what it was you in my life. Thanks a lot. Okay, so now I'm trying to give a more particular example of this massive gravity. It's about introduction of non-zero mass of graviton. And of course, it's also started with Valia, from Valia, because you know, this I mean, because he was the one who, I mean, discusses problem first in 1970. So it's just only 50 years ago. Okay, so let me start from this reminding the idea. I'm apologizing that I'm talking about very old stuff, and you know, probably most of you know all this stuff, but to me it sounds very good illustration, you know, what comes out of I mean, his breakthrough. Okay, so I mean, masses, no, this long range forces which is described by massive particle, it's you know, it seems always natural to consider them as a smooth limit of a massive series with finite range forces. Okay, in particular example is Feynman approach to gravity. He tried to quantize this gravity, but he started from non-abelian theory in '63, and for him, it was no doubt that definition of the theory could be done, you know, starting from non-zero mass of vector particle and then going to the limit of zero mass. Okay. I mean, no, as you probably know, all know that it works for spin 0 in 1/2 and even works for QET. But already in the non-abelian Young-Mills series, this limit of zero mass is non-trivial. There is no continuity if we are talking about hard mass of vector particle. Main difference for spin 1 is that spin 1 is the one which has more degrees of freedom than corresponding field. So for spin 0 and 1/2, number of fields is equal to number of degrees of freedom, while for spin 1 you have this longitudinal polarization for massive particle which is absent for masses. Okay, so I mean, as in standard model, again, as you know very well, that Higgs mechanism leads to continuity in mass, but the price for this is that you introduce extra field. So I will try to go along this line to give example with vector field first, and then go to graviton. But in gravity, the problem is gravity, which was discovered in 1970 by three authors, more or less very close in time: Iwasaki, it was one Dam and Weidman were second group, and Vale Zakharov was the third one. But as I said, it's all of the three probably were independent and very close in time. So if you consider this graviton exchange, which is equivalent to this kind of classical physics interaction due to gravity, then what was found that bending of light in theory with massive graviton is 3/4 of the one which predicted by general relativity when mass is equal to 0. Okay. So the limit, there is no singularity, but we can go from non-zero mass to zero mass, but the result is does not coincide with m equals 0 result. Okay, so here it's just reminding that that there are two s plus 1 polarization state for non-zero mass, and there is only one-dimensional representation with helicity h and minus h for mass equals 0. So that's why I mean this discontinuity starts from spin 1. I mean in number of states. Okay. Now when as I said, when spin equal 1, we have only two polarization state for m equals 0 and 3 states for m not equal 0. Okay, in case of QED for abelian field, I mean, again, I try to go faster with this, that you can check that while it is already occurred that, but this additional degree of freedom is the one which which interaction interacts with other with the matter interaction goes to 0 at m equals 0. Now here it is particular example that we introduce mass by Prokop formalism, adding mass storm, and we can use Stückelberg substitution to for this stuff, and then okay to see that I mean to keep gauge invariance intact, but it's just convenient way to relate longitudinal polarization with phi, but also in kind of in a normal form polarization you can see that in rest frame you have three polarization, you can boost them, and it is and then the boosting polarization, longitudinal polarization, has a form k mu divided by m plus terms proportional to m. So in interaction with the conserved current epsilon mu g mu, you know, this single term disappears and remaining amplitude is proportional to m. Okay. Now in case of non-abelian case, we can go more or less along the same way. Also consider this longitudinal polarization. Okay, maybe, I don't know, I hope that you can see it. It is the last line. And again, it's proportional to k mu. However, I mean singular term. However, so for emission of one vector particle, it would be the same smallness at m equals 0. However, when we consider the emission of two particles, then you know you have m from first step, and you have 1 over m from the second step. So when a commutator of color generator does not vanish, then you know this amplitude of emission of two longitudinal quanta does not vanish. Okay. Now, in terms of loops, it corresponds to appearance of problem at the second the problem appears already at the level of one loop. So where you have two particles inside, that contribution of longitudinal polarization does not disappear in the loop. Okay. However, it is in terms of field theory, it is still logarithmic in one loop, and say Martinus Veltman, who who consider this suggested that the theory would be normalizable even with hard mass of vector particle. And with Yurik Hiplovich in 71, we did try to follow this route to show that when you have more than two particles, then you have singularity, which is written here like energy divided by m in number of helicity 0 particle minus 2. And then it shows that starting from second loop, you already have non-normalizable theory. So, I mean, okay, in particular, we did formulate that Lagrangian of longitudinal polarization could be viewed as had a form similar to pi and chiral Lagrangian. Okay. This shows that the theory is certainly non-normalizable, and its coupling it is 1 over g original coupling divided by m, and there is singularity at m equals 0. Of course, if you know, of course, I mean, the natural step is to say, okay, let's go to linear sigma model instead of this chiral Lagrangian, and then the realizability would be restored. And it essentially it is what's happening in standard model. Okay, now I'm trying to to go to this Einstein theory of gravity. So when Valle and others put forward this idea that there is discontinuity at m goes to 0, you know, of course, I would say that it sounds kind of extremely unphysical, right? That that there is no smoothness in physics when mass is arbitrarily small compared with mass equals 0. Okay, so that's why you know, a couple of years later in 72 I decided to follow this route. Okay, I mean, and just to remind here that that to introduce massive spin equal to tensor field, one can add this so-called Pauli Field's mass storm written at the lower line, and I mean. And it gives you, you know, 5 in terms of particle. It would be 5 polarization associated with spin equal to, and and in quadratic approximation for Lagrangian, this form of Pauli fields is unique. Okay, now here you can see zero helicity state in the res frame. How it looks like. No, that's similar to vector field, but now you see that it is a trace of h mu equals 0. Okay, and if you go to the boost, if you boost this, then you will see that zero polarization has the form this mu over m square plus terms which are zero order in m. Okay, so in both cases, expansion goes in m square, but there it was 1 over m, and next term for vector field was proportional to m. Here, next term is not proportional to m. Okay, so it means that when we have interaction h mu multiplied by t mu, the first singular term disappears, but second term remains, and it is nothing but interaction with zero helicity of spin equal to, and zero helicity spin equal to does not in this interaction with the matter does not vanish in you know, even at m equals 0. No, in this way we can talk about emission of this zero helicity quanta, but when we consider exchange by zero helicity quanta, it must be you know, also non-vanishing and added effect of this discontinuity. Here it is exchange. So if we have zero helicity, I'm sorry, if you have zero mass, then that we know propagator of graviton written in the last line. Okay, and then if you will consider, I mean, we will see that essentially it is exchanged by, I mean, no, in terms of imaginary path, it can correspond to exchange by normal gravitons and gives you normal potential, Coulomb Newton potential for two interacting bodies. But when we go to non-zero mass, then you can see that propagator coefficient for this attenuated alpha beta atom is different, not -1 but 2/3, and potential becomes -4/3, which is natural because you have extra exchange by zero helicity. By itself, it would be not a big deal. You would say that just rename Newton constant, but it's important that there is also a space component of energy momentum tensor, and for light, for example, trace of energy momentum tensor equals 0. Okay, and it is this amplitude written here shows the difference, and so this 1/3 instead of 1/2 for m non-equal 0 explain why this I mean 3/4 of in this light banding. Okay, so now next step is of course to consider nonlinear corrections for this massive gravity case. So I mean parametrically one can see that if you consider this stuff those corrections, that correction would be singular in M, and it is the main point that because interaction goes. No, remember that h mu is kind of second power of energy. Okay, so you'll get this singular term, and it shows that at large energies interaction becomes strong, and okay, and there is a critical energy which is I mean given by product of m squared by mass of Planck of the power 1/3. Okay, in particular, you know, this line of reasoning was due to Kani Hamed, Georgi, and Schwartz in 02, but the way I try to approach it in 1972, you know, after various paper was to consider, you know, not just large energy, but consider interaction with a heavy source. So correction to, I mean, Schwarzschild. So the point is that if you consider these corrections in case of Schwarzschild, so it's a little bit different power, but still you will see that corrections are singular in M. Okay, so 1/m to the 4th appears as a correction, and this correction is simple that it is like iteration of the current. So in the video presentation, one graviton exchange in a nonlinear correction appears that you have the current twice. Gravity from this current produce another gravity, and it is the source of it is kind of loop, but not a normal quantum field CV loop. It is a loop for heavy source. Okay, so in this way I did arrive to this critical distance, which is I mean proportional 1/m in the power 4/5. But it is, as I said, it is different from previous this large energy. Only difference that instead of energy, once it m, which enters mass of the source. Okay, so I mean, if you will take mass of graviton, you know, limitation for the mass of graviton 10 to 1/10 to 25 centimeters from particle data group, then for the sun we get critical size 10 to 21 centimeters. Okay, so I mean we can discuss Hubble radius or whatever, but it's clear that it is not weak coupling anymore because corrections are not small but large. Okay, so what to do with this ultra strong coupling in the limit of small mass? Okay. The point they tried to persuade was that this kind of strong interaction would lead to self-screening, that this strongly interacting zero heuristic quanta would screen itself. Okay, no, I try to avoid, will try to avoid to discuss all this particular correction. It is explicit calculation in Schwarzschild case with corrections. But instead of expansion in perturbation theory, which is singular in M, as we discussed, we can try to follow expansion in the mass. So to look for a solution which are continuous in the mass in strong coupling. Okay, and here it is example of those solutions. So which are as you can see, actually in one of potentials that is non-analytic in Newton constant, and there is this critical radius that I mean where you have how to say some kind of halo of this helicity zero quanta around the source. But this halo is such that it's self-screen the effect in a sense that result for say bending of light returns back to m equals 0. Of course, I mean, if you go to very large radius, then you know this solution is not written there, so it could be that even it doesn't coincide with exponentially decreasing one. So that's why people discuss it a lot. What would be, you know, the Schwarzschild solution at very large distances, even if asymptotic is Minkowski space. Okay, so it was another problem which was discussed very also at that time by Bulwer and Deser about instability related to nonlinear appearance of the sixth polarization. So in field theory, in linear approximation for equation, it is consistent theory of massive spin 2, but if you go beyond linear approximation in equations, then you can see that spin kind of spin 0 degree of freedom will show up due to nonlinearity. Okay, and it was kind of I mean, it was some number, some activity associated with the fact how you can you know deal with this, and it appears relatively recently in recent years that okay, that in principle you can modify mass storm from Pauli fields in higher orders in such a way that keep 5 polarization without adding the 6th one. So this problem in certain sense is solved. Okay, I mean, to be closer to conclusion, I would like to mention Brane Gravity, where effect of similar to this, I mean, massive gravity appears, while it's not exactly the same as a hot mass of graviton, but it is very much similar effect. And also would like to mention that, say, you can try to ask yourself whether it's possible to make analog of Higgs effect for graviton, to make kind of continuity in the mass similar to how it was done for standard model, where you introducing additional degrees of freedom, particular Higgs field, and making transition to n equals 0 possible. Higgization in gravity, in certain sense, implied breaking of Lorentz invariance, because you know there it was condensation of certain charges in standard model. Here, it is momentum and or angular momentum which plays this role for gravity. So that's why. But still, if you ready to break Lorentz invariance, then it's possible. Okay, I believe that in particular Valery Bakov, if he is still here, he does probably remember that they discussed this in case of breaking Lorentz invariance for vector field. So in case of vector field, I mean, once you do not support Lorentz invariance, then it's not a big deal. So it's rather easy disconnect this instantaneous interaction and exchange by transversal quanta, and it was a difficulty. I mean, when it was Lorentz events preserved, but once it's not preserved, then it's very much possible. So here it was example for vector field, which but a similar one could be for gravity as well. Okay, so I'm coming to my conclusion here. It's about this massive modification of gravity. People also discuss certain application of this, so you can try to discuss modified gravity to explain, you know, some stuff in astrophysics as well. But I don't know, the way at least was started by Vale and I try to continue was more kind of on field theoretical side. That whether it's possible or not to make it continuous. Okay. No, it's, as you see, it's not kind of how to say, it's not because it's a strong coupling. It's not could be considered as this mechanism of self-screening could not be considered as a proven one. So it's contains all this problem. Okay. So there is no much of theoretical control here, but I mean, still, I mean, this possibility that I mean, something like, you know, hidden strong interaction in weak gravity is possible due to non-zero mass. It's interesting, and particularly interesting is this Lorentz breaking condensate as well, but for different phenomenology. But I'm not going to go in the details here, and I will stop with my thanks to you for listening. Thank you.
Thank you very much for a very interesting talk. Thanks. Well, just questions, comments now to this. I think just we can take something. Well, I will take something. Well, now I see Nugzar.
Hello, everybody. Thing is that gravity or technique of curved space is a mathematical method. You may use gravity language, even elasticity theory of body. So similarly, in some dynamics, you may invent gravitational methods, including QCD. You may remember Salam Neyman invented so-called strong gravity for hadrons. And in a sense, it was successful qualitatively. Hadrons with confinements you can interpret in geometric terms. So formally, gravity methods works even hadron physics. Thing is how to use them. So strong gravity as a model on the level of non-Abelian and others are on the same level. Thing is how to use. I hope they are useful. Thank you. It's a comment.
No, I agree that you know, this Salam Srazdi approach, they did not apply it for massive gravity, but of course you can just say that you know that you have this dual gravity, and you know they imply it for hadronic physics, right? I mean at that time, right? But people then in terms of discussing you know this massive gravity, they did use the same you know their ideas and apply it for I mean for discussion massive gravity as well, right? So but I agree completely. This is kind of, I would say, more technical, right? That you instead of saying fields Pauli fields mass storm, you can refer to you know this Salam Celesti. Okay, and yeah, but yeah, so it's certain too. I agree.
Well, actually, concerning just applications, recently we had a seminar talk in Dubna on the occasion of this year Nobel Prize. And the speaker was Alexander Zakharov from ITEP. And he said that, well, massive gravity developed by Zakharov, and he made remark, but not by me, is very much just studied and tested and so on. So this is very active in the, I mean, in the astrophysics and cosmology. But I think this how this comes. I think for me it's quite interesting and funny. I would say. Well, just okay. So let us thank Arkady